Hello, and welcome to my fourth video. It's been a little while since I made a video, but thought I might get back into it. And let's see, in this one I wanted to go over calculating the density necessary to form a black hole, and in doing that we are going to also calculate the radius of an event horizon for a black hole, and we're also going to do some cool orbital mechanics. So, could do a lot today. Kind of exciting. Um, Anyways, let's start out with the basics. So, to form a black hole, we need some point, or something, with mass. Mass. And we're going to call that m for now, right? Now, given enough mass, we could form an event horizon. But how do we actually calculate the radius of an event horizon? I should say, before we get into this, an event horizon is kind of a radius around this mass where the gravitational attraction force is so strong that not even light can escape it, so you kind of get like this black sphere around it. I wonder, maybe I'll draw that in green, kind of around, actually no, yeah, yeah, I'll draw it in green. So you kind of get like this sphere around it where not even light can escape. And our goal is to calculate that distance, the radius. To do that, we would start with developing an equation to calculate escape velocity. And a good way to do that is to look at the equation for calculating mechanical energy of a body being acted upon by gravity. And initially, I'm going to give you the equation, and then we'll explain it. So let's say we have some other body over here, and it is some distance from our mass. We'll call that distance r. And I'm going to label that as vector r. For reference, if I'm writing r without the vector notation, then that just means the magnitude of r. And then it also maybe has some velocity that we will call vector v, like that. Now, the mechanical energy of this point, so em equals 1/2 v squared minus mu divided by r, where mu equals our gravitational constant multiplied by m, the mass of that attracting body. So you can see from this equation that we're kind of adding together the kinetic energy and potential energy. This bit is, of course, kinetic energy, so we'll call that EK. And this bit takes a little bit of explaining, but we'll go over it. This bit right here is actually our potential energy, so I'll call that EP. So kinetic energy you can kind of see, right? EK equals 1/2 mv squared. Although we can get rid of our m here because we're calculating specific mechanical energy, so that's per unit of mass. So we get 1/2 v squared. That's our kinetic energy. Now potential energy is a little trickier, but we can derivate it. So initially, let's just look at how we calculate energy. Energy equals our force times delta S, or the distance that that force was acted upon. So visually we can kind of see, okay, this is almost like calculating the area of a rectangle, right? Where this side length is F, this side length is delta S, and we're just kind of calculating that area, right? That's kind of like what that's saying, just multiplying two things together. However, what if our force changes with distance? And this is exactly the case with gravity. So as we get closer to the body, we have more force acting upon us, and as we're farther away, we have less force acting upon us. So in reality, instead of calculating a rectangle, we'd be calculating something kind of like this. So we have F, that's that length. We have delta S. But instead of a rectangle, we have something a little bit more like that we'd be calculating. right? So you can see, let's say this is 0 distance. As we're really close to it, right, then we have more force acting upon us. As we're really far away from it, we have less force acting upon us. So now instead of finding just this area of a rectangle, we're finding this area of kind of a weird, almost bent triangle shape. Now, luckily, we can actually define this curve as a function of distance. So for now, I'll just call that f as a function of delta s. And that means to find this area, all we have to do is integrate that. So that area, so indefinite integral f delta s with respect to delta s. So that gives us the area. Now, hang on, we just set up here that that area equals our energy, right? So this equals E. Kind of handy. Now, for a gravitational situation, we can calculate the force of gravity. So I'll do Fg. And I'm actually going to use R here instead of delta S. R is usually used in orbital mechanics to denote distance. We could use delta S here if we wanted, but I'm just going to switch it to R. But know that R and delta S represent the same thing. So we can calculate our force of gravity equal to mu divided by r squared. And remember our definition of mu up here is our gravitational constant multiplied by our attracting mass. And here I'll write a little note off to the side that r equals delta s. They're the same thing. So now, to find how much energy we're getting from this, how much potential energy, all we have to do is integrate it. So we do the integral of f g r. Oh, and I should say this definition of gravity just comes from the Newtonian calculation for gravity, kind of decreasing with the inverse square of distance. So we integrate that with respect to r, right, which is what we decided to do up here. So that is equal to the integral of mu divided by r squared dr, which then equals negative mu divided by r plus c. And you can manually calculate that to verify my work if you would like. And our c is, of course, our integration constant. Now, this kind of relates to the reference point for our potential energy, because, of course, gravitational potential energy needs some reference point. So what we can do is just set the c equal to 0. And that's almost setting, like, infinity equal to our reference point, so infinitely far away from our mass. Now, one downside of this is it means our potential energy will always be negative, but we can deal with that. So we can then basically just say this is negative mu divided by r, which equals our gravitational potential energy. And you can see, sure enough, in our equation, we have negative mu divided by r. So this is just kinetic energy plus oh, what did I just do? There we go. This is just kinetic energy plus our gravitational potential energy. Oh, one thing I should also explain. You might be used to gravitational potential energy, so EP equal to mgh, so mass times gravitational acceleration multiplied by height. And this is true as long as we stay close to Earth, but as we get farther and farther away, this is going to become inaccurate, because that equals our force of gravity when we're close to Earth, but as we get farther away, that force of gravity is going to change, making this equation inaccurate when we're far away from an attracting body. So now from here, we can calculate our escape velocity. I'm going to make a little new section for this. Escape velocity right over here. So what do we know about when a body escapes from the gravitational pull of an attracting body? Well, let's look at one specific point in that orbiting body's lifetime. And that is when it is infinitely far away from that attracting body. So in this case, r equals infinity. Well, that means we have fully escaped, right? So our gravitational attraction is going to be equal to 0 because we're infinitely far away. Remember, this is never actually going to happen, but we're going to approach it infinitely. Because obviously you can never get infinitely far away from something, but you can get really darn close to it. So assuming we are infinitely far away, we know that our velocity, so v, has to equal 0, right? Because we're assuming the minimum escape velocity. So if we fully escaped it, we should have no velocity left over. So we can plug this into our energy equation. So em equals 1/2 0 squared, because remember velocity equals 0, minus mu divided by infinity. And oh look, this goes away to 0, and as does this, because if you divide something by infinity, or as you approach infinity, that's going to go to 0. So we actually have 0 mechanical energy, which I always found really interesting, equals 0. So now what we can do, because we know that's equal to 0, is say, okay, well that means that if we're going to escape, we need our mechanical energy to equal 0. So 0 equals 1/2 v squared minus mu divided by r. So what's kind of cool about this is, say we want to escape from an attracting body, and we know our current and we know our current distance from the attracting body, so we know our r value. Well, by rearranging this equation, we can then find the necessary velocity. And vice versa, if we know our current velocity, we can find our necessary distance. So one more rearranging of this, just to get it in a bit of a nicer form. Mu divided by r equals 1/2 v squared. Just to get that in a little bit of a nicer form. So that's kind of cool. That's how we calculate escape velocity. So now let's get on to calculating the event horizon. So event horizon radius. So the radius of our event horizon here. Well, we can apply this, because this is our escape velocity, right? And we want to calculate the radius in which light cannot escape. So we know our velocity. Velocity equals, not 0. Velocity does not equal 0. Velocity equals c, where c is our speed of light. So what we can do, and I need to underline this as well. So what we can do then is say, okay, plugging this into our escape velocity equation up here, we know mu divided by r equals 1/2 c squared. Kind of cool, right? So doing a little bit of rearranging of this, we can solve for r. So let's see, we have mu divided by 1/2 c squared equals r. Just rearranging this a little bit, and then we can bring that 2 up to the top from the 1/2. So we have 2 mu divided by c squared equals r. And that is our radius of an event horizon. So for reference, this is the minimum escape velocity. So we can go greater than this and still escape. So if r is greater than or equal to 2 mu divided by c squared, then light escapes. And then we can see it, because it has escaped the gravitational pull. Now, if r is less than 2 mu divided by c squared, light does not escape. So light does not escape. So then we can't see it because now it's stuck orbiting this mass, and that's where we get that kind of black sphere around a black hole, because no light within that radius can escape. So that's kind of cool. We just calculated the radius of our event horizon. Quite exciting. Now, as promised, our final goal was to calculate the density of a black hole. So, for something to be a black hole, all of the matter, or all the stuff that's causing gravity, has to fit within its event horizon, so the event horizon is visible, right? That's how we form a black hole. So let's write down what we know. I'll make a new section for this as well. Density of a black... Ooh, that's a terrible K. Black hole. Right, density of a black hole. So, we know that density equals mass divided by volume. And we can actually calculate our volume. So we know that all of the stuff has to fit within this sphere of the event horizon, right? So by calculating the volume of that sphere, we can calculate the necessary volume, right? So if you remember volume of a sphere, and actually maybe I'll make a little diagram for this. So we have in three-dimensional space, we have some sphere, right? Sorry, my artistry skills are not amazing. Oh, actually, you know what? That sphere doesn't look half bad. Maybe I take back what I said earlier. Maybe my artistry skills aren't bad. Oh wait, actually no, it is a little lopsided. Okay, well, you get the point at least. And this is R, right? So our event horizon radius. Well, we can calculate the volume of this event horizon sphere. So V equals 4/3 pi R cubed. Slight side note, there's a really cool derivation for this that uses integrals. Strongly recommend looking at that. That was kind of fun to do. Yeah, anyways, a little side note. But we actually know R, right? Because we calculated it with our event horizon radius over here. So we know that R equals 2 mu divided by c squared. So remember that mu equals gm, so our gravitational coefficient multiplied by our mass. Well, now we can rewrite density over here by saying, well, okay, density equals mass divided by... Oh, I probably shouldn't have made that v, because that could get confusing with velocity. Anyways, well, you guys know it's volume for now. Know that this v here is volume. Probably should have changed that, but oh well. But we know our volume is equal to 4/3 pi r cubed, but plugging in this definition for r, we get 2 mu divided by c squared, right? Now, what's kind of cool is because mu equals gm, oh, and sorry, that should be cubed. So what's kind of cool is because mu equals gm, we can actually pull one of these out, because ideally we want to get rid of this mass. Now, our final equation, fingers crossed, with a bit of luck, should be density in terms of radius. So we want to make a black hole of a certain scale, if you will, and this equation will then say the density necessary, the minimum density necessary, I should say. So this mass is kind of getting in the way because we don't actually know the mass and we don't really care about the mass too much. We just want the size and density. But there's a kind of cool little method we can use to get rid of it. So what we can do is then rewrite this again as d equals m divided by 4/3 pi and then 2 mu divided by c squared. Now I'm just going to square this and pull one of these out. So 2 mu divided by c squared. You'll see why I do that in a minute. Remember how mu equaled gm? Well, we can replace this mu with gm. Right? That'll still be accurate. Now, what's kind of cool is that means this m and that m cancel. So we end up with d for density equals 1 divided by 4/3 pi. And I'm going to convert this back to r, so we get r squared. And that multiplied by 2g, that looks a bit like a 6. 2g divided by c squared. Now we can do a bit of simplification on this, just combining this 4 and this 2, combining this 4, this 2, moving this 3 up to the top, moving this c squared up to the top. We get d equals 3c squared divided by 4 pi r, oh wait, sorry, that should be 8 pi r squared multiplied by g. And that is the density of a black hole. Anyways, I kind of love this problem. I always find it super, super fun to do. Because it just kind of builds on itself. You like calculate the mechanical energy of an orbiting body, then you calculate the escape velocity, then you calculate the event horizon radius, and finally you calculate the density. And it's so satisfying to just see it all build up to one final equation. And it's actually a relatively simple equation. It's nothing too crazy in the very end, which makes it all the more satisfying, really. But before you go, though, I did make a little Desmos graph thingy depicting what we went over. So it has a little model of a black hole. You can see the event horizon in black right there. The orange around this shows the trajectories of escaped light. That we didn't cover in this video. It's a little beyond the scope of this video. But maybe I'll make another video with that in. That could be kind of fun. Yeah, maybe I'll make another video with that in. But yeah. Anyways, I have this link to the Desmos in the video description, so make sure to check that out if you're interested. And yeah, thank you very much for watching. I'm hoping to get a few more videos out before I head off to university. So hopefully see you guys again before then. Bye!